Iteration and the Newton-Raphson method are two ways in which we can try to create approximations for a point or solution of a curve or intersecting curves. In the case of iteration, what we will end up having is an equation which is x equals and then some other expression which also contains x. So you would put in some x naught into the bigger expression and get out an x1 on the other side. This x1 you would then put back into the other expression to get out an answer of x2, and so forth for as many times as the question asks. We'll get on to an example of that in a second. But to begin with, just to show graphically what would be happening if, say, we were using iteration to find the point of intersection between two curves. What you will have had is some equation which has these two lines equations equal to each other and then brought onto the same side, and from that you would have some starting x value. Let's say this starting x value was here. Now when you put that x value into the equation, this would give you some value here. Now from this point we would essentially be going up to the next line and then take that across until you hit the original line again. From here we would go down to this line here, where that would then be your x2 if that was x1. From here we then go across again until we hit the curve about here-ish for x3. This would come up here and so forth here for x4, and you'll notice we are gradually spiraling inwards towards this center point here, which would be the point of intersection. When it comes to plugging numbers into the equation, you don't have to worry about how this is happening. This is what it would look like on a graph, but it may just be that one time you're asked to show graphically what is going on. So yes, you'll end up with this cobweb-styled spiral coming inwards towards the point of intersection. If you didn't end up spiraling towards that point of intersection, that would just mean you had the incorrect starting x value. But anyway, on to just the more numerical side of things. If, say, we had this function that's x cubed plus 2x squared plus x plus 1, we would first of all want to show that a root lies between minus 1.5 and minus 2. Then we'll show that x equals minus x plus 1 over x squared plus 2 if f of x equals 0. Then use iteration with x naught being minus 2 to find values for x1, x2 and x3. And then finally use a suitable interval to prove this root is minus 1.755 to 3 decimal places. The first of these instructions, showing that a root lies within a given interval, relies on you then plugging these x values respectively into fx. So to start off with, if we were to do minus 1.5 cubed plus 2 times minus 1.5 squared plus minus 1.5 plus 1, that would get you a value of 0.625. Now if we did it again with the minus 2, so minus 2 cubed plus 2 lots of minus 2 squared plus minus 2 plus 1, that gets you minus 1. So when we have an x-coordinate of minus 1.5, we would get a y-coordinate of 0.625. Yet if we just go the tiniest bit to the left and go to x being minus 2, we now have a y-coordinate of minus 1. Unless this graph is going to have an asymptote like the tan graph, that is to say a point where the curve doesn't touch, instead it tends towards infinity in one direction and then comes back into view from the other direction, which it won't because this is a continuous cubic graph, we have to have crossed the x-axis therefore in order to get from this y value to this y value. This would be the root. When we say the solution, the root that is where we are crossing the x-axis. So the fact that we have had a sign change tells us that the root lies between those x values. Then, to show that you can create this expression if fx equals 0. Well, if fx equals 0, then this equation equals 0, and so we can move most of these terms over the equal sign and get the minus of them. So that if we just left the x cubed on its own, that would then equal the negative. And rather than just doing the negative signs of all of these, because the thing we're trying to show is in a bracket with a negative in front, I'll just keep it in that form as well. So minus all of the 2x squared plus x plus 1. From here, just to get a single x on its own, we'll divide by x squared. Well, 2x squared divided by x squared is 2, and the x plus 1 divided by x squared is x plus 1 over x squared. We have them the other way around what we wanted to show, but because it's addition, that doesn't make a difference. We have shown it. Thirdly, use iteration with x0 being minus 2 to find the next 3 iterations or approximations. In that case then, well, your x1 is going to be minus, so the minus 2 plus 1 over minus 2 squared plus 2. That would give you, in this case, minus 1.75. If we were to take this minus 1.75 and plug it back into here, so now minus 1.75 plus 1 over minus 1.75 squared plus 2, that gets you an approximate value of minus 1.755 if we were to round to 3 decimal places. And if we took that exact x2 value, so keep it unrounded on your calculator, and put that back in, you'd get an answer for x3, which also rounds to 1.755 to 3 decimal places. Now, it may seem that this then should give an indication that that is going to be the root to 3 decimal places. Yet, the question is specifically asking us to also prove this using a suitable interval. What we mean by a suitable interval is if this has been rounded to 3 decimal places, there will be a lower bound and an upper bound just in rounding in general. So if we were to get the values for the lower bound and the upper bound that had allowed it to be rounded to 3 decimal places this way, we should once again find a sign change. So if we were to do that when x is equal to minus 1.7545, which would be the lower bound, because this would round up to 3 decimal places to be 755, you find fx having an approximate value of 0.00122. And then if we were to do x being minus 1.7555, which would be the upper bound, then fx ends up being approximately minus 0.002. We have indeed had another sign change, wherein we had the upper and lower bounds of it being listed 3 decimal places. Therefore, the root must indeed be that, rounded that way. If that makes sense, we can see how we will have rearranged an equation to get x equals something else with x in it, how you could use an interval to show a sign change which indicates that the root is indeed within that interval, and how we can then use kind of a combination of the two with the actual iteration process. We take a starting x value, plug it into the equation, get an answer out, and then plug that back in to get another answer and so forth. If that makes sense, let's just see how you might get along with an example of your own. So here instead, we have f of x equals e to the x plus 2 plus x minus 10. So show that x equals ln of 10 minus x minus 2 if fx is equal to 0. Then use iteration with x0 being 0.5, find x1, x2 and x3. Then wrap up by using a suitable interval to prove that the root is 0.275 to 3 decimal places. If you want a refresher about e and ln, you can look at the logarithms and exponentials video. But other than that, if you pause the video and just have a go at this for yourself, trying to repeat the kind of steps we did above, then press play again when you're ready to compare. So, to start off with the rearranging. Here, we're going to be trying to get the x on its own. It could be either one of these x's, but because we're going to be introducing an ln, we're probably going to be looking at the x in this power here. So, because fx equals 0, like above, we can now move all the other terms onto the other side of an equal sign. So we end up with e to the x plus 2 equaling this minus 10 would become positive, and this x would become negative. Okay, so we've already got what's going to be in the bracket. And then to lower a power down to be the main part of the equation, you'll use logarithms. So your x plus 2 equals the ln of the 10 minus x. And then here we can just move that 2 onto the other side, making it a minus. Therefore, we have shown this expression. Then, for using the iteration, we'll start off just by putting that x0 in there. So we'll find that x1 equals the ln of 10 minus 0.5 minus 2. Putting that in your calculator, you're going to get a value that's approximately 0.251. Taking this 0.251 and putting that back into this equation again, you get that x2 is approximately 0.277. And then taking that 0.277, putting it in, you get an x3, which will be approximately 0.274. Now we can see here that we are potentially tending somewhat towards a value because the gap between these numbers is getting smaller and smaller. However, unlike in the previous question, we're definitely not near a consistent value quickly. We would have to keep on going and going if we wanted to find that, which you could. But the question isn't requiring of you. Instead, it wants you to go straight to proving the root is that to 3 decimal places using the interval. So we need a lower bound and an upper bound. The lower bound would be if x was 0.2745. If you do that, then the f of x is going to be approximately minus 0.00244. And if you did the upper bound of x being 0.2755, you end up with f of x being approximately 0.00828. This is a negative, this is a positive. We have had a sign change, therefore the root, the point where it crosses the x-axis, must indeed happen between here, which would round whatever it is to that value of 0.275 there. If we're happy with that, and we're good therefore with what iteration would be, let's move on to now talk about the other method I mentioned, Newton-Raphson. Now, the Newton-Raphson method has the following formula, that the next x value that we'd get through, because again we're going to be putting in an x value and getting out an answer that you put back in, the next x value is the current x value minus the original function divided by the differential of that original function. So we're going to be getting now into differentiation again. What happens when we do this is if we were to find some starting x value here, this we would take up to this point on the curve here. What would be happening is we'd end up with a tangent to the curve going through this point, which would then hit the x-axis here at x2. Going up here, that leads to a new point on the curve. Once again, a tangent would be drawn, and this would ultimately hit the x-axis now at x3. So we get another point on the curve and another tangent that now hits this x4 here, and so on and so on. And as you can see already here, we'd basically just be almost stopping instantly with our tangents because we're so close to the x-axis now, we're barely going to change anymore. This would be our good approximation of that root. The other thing to note here, if it becomes important, for instance, if we have a trigonomic function in our equation, is that Newton-Raphson only works with radians. So, yes, make sure that you're in that setting if you are going to be doing Newton-Raphson. With that in mind, though, let's just look to yet another example question. So 2x cubed plus x squared minus 1 equals 0 is our starting curve equation. We want to show, first of all, that x equals 4x cubed and then the n just being this n from here, plus x squared n plus 1 over 6x squared n plus 2xn. Then if x1 equals 1, find x2 and x3, and explain why for this question we cannot use x equals 0. Well, to start off with, if we are going to be doing the Newton-Raphson method, we need to start by differentiating. So the differential of that equation would be 6x squared plus 2x. Therefore, your next x along is going to be just x minus, I'm not going to bother doing all the n's, but the you don't need to with the working, just acknowledge that's part of the general formula. So your original function of 2x cubed plus x squared minus 1, and then this will be divided by the 6x squared plus 2x. Okay, so we have our denominator, great. But we have two separate terms, which also explains why the numerator is different. In order to combine these into a single fraction, we'll need to make this a fraction over the same denominator. So this would be 6x cubed plus 2x squared over 6x squared plus 2x. So it's basically the denominator just times by an additional x, minus that same fraction from before. And so, just collecting the like terms, 6x cubed minus 2x cubed is 4x cubed. 2x squared minus x squared is just going to be x squared. And then minus 1 is plus 1. This being over still the 6x squared plus 2x. Now that we've shown this, if we are to start plugging in x values and getting values out, your x2, because when we're starting with x1 this time, per the wording of the question, you would have 4 lots of 1 cubed plus 1 squared plus 1 over 6 lots of 1 squared plus 2 lots of 1. This would give you a value of 3/4. If you then put that in for this x value here and to get x3, you would end up obviously with your 4 lots of 3/4 cubed plus 3/4 squared plus 1 all over 6 lots of 3/4 squared plus 2 lots of the 3/4. This would get you a value of 2/3. So then explain why in this question we cannot use x equals 0. The reason why we can't use x equals 0 is because if x equals 0, then this gradient here, the differential, would equal 0 itself. Yes, and if the gradient is 0, you would end up with just a horizontal line here, and a horizontal line is never going to cut the x-axis, so you would never get a solution to this method. So we can never use an x value that would make the differential, which would make the gradient, equal 0 as well. If we can see what we're doing here, if to wrap up with then, we once again just see how you get along with an example of your own. Here, the f of x is sine 2x plus ln x. Show that there is a stationary point in the interval 1 and 1.1. Use Newton-Raphson method with x0 being 1.05 to find the approximation for the stationary point x2. So, here we are working with trigonometric functions and natural logarithms. If needs be, you may just want to double check how we're going to be differentiating those. Remember now, unlike with the regular iteration, we do need to include differentiation as well. Also just see if there's anything different in the wording of this question which may imply you need to do any step slightly differently. Either way, just have a think about it, pause the video, have a go for yourself, and then press play again when you're ready to compare. Right, so once again, we'll start by differentiating this original function. So the differential here would be so. When you differentiate sine, you're going to get cos, but also you're going to times by the differential of what's in the bracket. So here, 2x differentiated as 2, So together that means we have 2 cos 2x, and then ln x differentiates to 1 over x. With this differential, we can now start to see if there's a stationary point within this interval. This is different to what we had to do before because we're looking for specifically a stationary point, not a route through the x-axis. So here, it's not that the y-coordinate equals 0, it's that the gradient equals 0. So it's this expression equaling 0 that we're looking for an x value for. So if we now do this first of all, where x is 1, so 2 cos 2 lots of 1 plus 1 over 1, and remembering that because this is Newton-Raphson, we have to be in the radians setting of our calculator. This will get us an approximate value of 0.168, and if we do it again, where now the x is 1.1, that gets us an approximate value of minus 0.268. Here we have a sign change, therefore the x value that makes the gradient equal 0, the stationary point, must indeed lie between 1 and minus 1. Now then, because we're now looking for the approximation for this stationary point, this differential here is like our main function now. So in order to get a divide by the differential of the thing the x really belongs to, we're going to have to differentiate again. We need a second derivative. So here, if we get a second derivative, cos differentiates to minus sine, and once again you times by the differential of what's in the brackets. So we end up with minus 4 sine 2x, and then this, because this is like x to the minus 1, that is going to differentiate to minus 1 over x squared, or minus x to the minus 2. Plugging these equations into our Newton-Raphson method, we'll get that the next x value along is going to be x minus 2 cos 2x plus 1 over x, all over minus 4 sine 2x minus 1 over x squared. Plugging in this x0 value of 1.05 into this whole thing, that gets you an approximate value of 1.037. Then taking what would be the unrounded version of this from your calculator and putting that in, that gets you an x2, which is where we're trying to get to, approximation of the x-coordinate of the stationary point being 1.037, yet again, both of these rounded to the exact same thing. Hopefully we can see here the distinctions between iteration and Newton-Raphson method, as well as the similarities in how they're going to be repeatedly putting values in to get new answers, and how they can be used to find approximations for solutions to certain things. There's differences in how you derive the equations that you'll be plugging your x values into, but once you have them, it's just a matter of repeating and repeating. It may help perhaps when you put it in your calculator to, rather than writing like the actual decimal value, just to type in answer with the answer key. So then you can just keep on hitting equals and equals rather than having to retype out the decimal each time. Just a thought if it helps.